Another important result, we have the union of connected subspaces of a topological space X. The union of connected subspaces of X having a point in common is connected. So how does this thing look like? We have the union of connected subspaces. So we are going to let X alphas be connected. We have connected subspaces of a topological space having a point in common. So these connected subspaces, they have a point in common. So if I let P be in the X alphas, so how does this thing look like? I have X. This alpha is from the indexing set I. I have X alpha 1. It has a point P. It has a point P. Also another X, X alpha 2. It also contains point P. Another X alpha 3. It also contains point P, and so on and so on. So what are we saying? We are saying that the union of these X alphas, is a connected subspace of a topological space X. That is what we want to prove. So by virtue of this diagram, you can easily see it that actually this union, the union of X alpha 1, alpha 2, alpha 3, will be connected. You cannot, as long as their intersection is not empty, as long as we have a point in those X alphas, yes, then their union will be connected. So we are going to prove that by contradiction. So we are going to suppose that Y is the union. This is the theorem. Let alpha be in the indexing set. Suppose that X alpha is connected, the intersection is non-empty. That means they have a point in common. The intersection is not empty. Then Y, which is the union, is connected. So we are going to prove this by contradiction. Proof. By way of contradiction, suppose that Y is not connected. Suppose that Y is not connected. What does this imply? This implies that there exists open sets. A and B. Open sets in X. There exists open sets A and B in X. In Y, sorry, there exists open sets A and B in Y, where A and B are non-empty. They are distinct, disjoint. There exists open sets A and B which satisfy those properties such that our union is now having a separation. Suppose that Y is not connected, so we can express Y as a separation. We can write it as the union of two open disjoint subsets of Y. What does that imply? So Y is not connected. Remember, this implies that this Y was our union. So we have the union alpha in the indexing set X alpha. This is equal to A union B. But these x alphas, they have a point in common. They have a point in common, and we are saying that these x alphas, they have a point in common. This point P, they have a point in common. And this is the union. Now we are separating this union. We are writing this union as a union of two disjoint open sets. As in, we are expressing it in terms of separation. We are separating it in terms of open sets A and B. We are separating the union. So what does that imply? So this implies that the common point P in the intersection, either lies in A or B. Because now we are saying that we can separate this union. So if we can separate it, then P either lies in A or B. Either lies in A or B. So we are going to suppose, without loss of generality, suppose that P is in B. So suppose that P is in B. Suppose that P is in B, then we are going to consider an arbitrary x alpha. Then P is also, because the intersection of these x alphas is empty, as in they have a point in common. So if we consider an arbitrary x alpha, also P is in that x alpha. P is in that x alpha. And what do we know about this x alpha? So P is in x alpha, and x alpha is connected. So P is in B, P is in x alpha, and x alpha is connected. And x alpha is a subspace of Y. X alpha is subspace of Y, which is connected, and Y has a separation. So by the preceding theorem, we have proved that, in the previous video, we have proved that we cannot have a connected subspace lying across a separation. So X alpha is a connected subspace, so it cannot lie across a separation. So it should either lie in A or B. Now, since P is in B and P is in X alpha, now X alpha will be contained in B. Then by the previous results, comma, we have X alpha as a subset of B. So we have X alpha as a subset of B. So this implies that for all alpha in the indexing set I, we have X alpha being a subset of B. So this implies that all the connected subspaces of a topological space Y, they are going to be lying within B. It's like we had something of this sort. Then we separated it into A and B. And remember, these X alpha 1, alpha 2, alpha 3, they have a point in common. So if we separate now the union, that point which is in those X alphas can either be in A or B. So we assumed that it is in B, And since it is in B, we have considered an arbitrary x alpha, so that x alpha also contains that point P. By the previous results, since x alpha is connected, it cannot lie across a separation. So it will be lying in this open set B. And that implies that since x alpha was arbitrary, so this implies that for all the alphas in the indexing set, we shall have x alpha in here. So that will imply that this open set A is now empty. So what does that imply? So this implies that A is an empty set. This is a contradiction. The contradiction. A is an empty set. This is a contradiction to the fact that A and B form a separation. They form a separation of Y. Contradiction, the fact that A and B form a separation of Y. Since they form a separation of Y, then they shouldn't be, both of them shouldn't be empty sets. A is non-empty and B is non-empty at the same time. So if you're having A as an empty set, then A and B cannot form a separation of Y. So what does that imply? So this implies that our assumption was actually wrong. This implies that Y now is connected. We cannot have A and B forming a separation of Y